Final video recording on capacitance, and hopefully from the previous simulation you saw that when we discharged the capacitor, the voltage and the current displayed what we call exponential decay. So the graphs of voltage against time were a curve which looked like this. Now current was negative, but just ignore that in this instance. This is the magnitude of the current. It actually turns out that the charge against time graph is also an exponential decay. So and not only can we solve problems using the graphs of voltage, charge and current against time, we also have to know how to use the mathematical formulae. And it turns out that the formula for the voltage against time is given by an exponential function. V equals V0 e to the negative t over tau. I'll come back to what tau means in a second. Q is equal to Q0 e to the negative t over tau, and I equals I0 e to the negative t over tau. What's this number tau, I hear you ask? Tau, which is common to all of them, is equal to the resistance times by the capacitance. Remember, this is a RC circuit, so we have a capacitor C connected to a resistor R. One side, which is the charging side, and then when we flick the switch, we have the discharge side. And we saw from the simulation, and you will hopefully be able to investigate by playing around with these parameters, that both by increasing the capacitance and the resistance, you increased the time it took for the functions to decay, therefore increasing tau, increasing either the resistance or the capacitance, increases the decay time. Now we could ask ourselves, just like with radioactive decay, what's the half-life, or how long would it take for the potential to reach half its initial value? So what time would it take for V0 to reach V0 divided by 2? Well, for that we have to solve an exponential equation. We'd put, taking this formula here, start with that one, we put V equal to V0 divided by 2 equals V0 e to the negative t½ for half-life divided by tau. Now the V0s on either side cancel, we're left with just ones, and because we have an exponential function on this time, to get rid of the exponential we have to take natural logarithms. So ln of v over 2 equals ln of e to the negative t½ over tau. Ln of e to the something is just the something, so we're left with, sorry, it shouldn't be a v0 there, it should be a half. Ln of a half equals negative t½ over tau. Ln a half is the same as negative ln 2 equals t½ divided by tau. Therefore, I've kind of run out of space, I'll write it up here. Remember that tau equals R times C. You're also given that in your data booklet. The half-life, the time it takes for the voltage to decay by half, is equal to tau times ln 2. So basically the time, the decay time, is directly proportional to tau, which is the resistance times the capacitance.